Today is the 11th of September, and we are in Chapter 2. We're going to talk about what happens to materials when they are exposed to temperature changes. And we're going to do a little bit of math with that, and then we're going to start talking about a generalized form of Hooke's law, which brings into the idea of what happens on the transverse faces when we put an axial load on a structural member. And that actually gets us almost to the end of what we're going to cover in Chapter 2. We're going to do a little bit more on Wednesday, and then we'll do a little bit of a review and get ready for the quiz on Friday, and we may start the next chapter just conceptually, not mathematically, but we may start that on Friday. So let's talk about section 2.3. I don't like this pen. It's bugging me already. And in section 2.3, we talk about problems that involve, oh my gosh, got to be kidding me. Try again. Problems involving temperature change. See, if you pick up a bad pen, what you need to do is to put it down, and then if you pick up a worse pen, you can lower your standards and go back to the first pen, and it will be just fine. So there you go. So we talked about last time, if we have a situation, this was not about temperature change, but if we have a structural member, for example, this one is attached to a ceiling, and if I pull on it and I have a reactive force at the ceiling, that we will get some sort of a change in length. Well, that would be excessive, but I'm just showing that we would call del. Or if we push on it, we would get a negative del. So in other words, sigma is related to a change in length if we are talking about an applied load. There's sort of an interesting thing that happens if we have a structural member that is subjected to a temperature change. And although we don't really design that much with concrete, if this is the side view of two paving stones or two pieces of a sidewalk, we always have an expansion gap in between them because sidewalks specifically are subjected to changes in temperature due to the fact that you can't bring in your sidewalk at night, and it gets cold at night, and it's hot during the day, and it's hot in the summer, it's cold in the winter. And what happens when the temperature increases, when you have a positive delta T, pardon me, you will have an expansion where each of these will lengthen, and if you have a negative delta T, you will have both of these contract. And that del is not associated with the stress. Del due to temp is not associated with a stress unless we restrict it, unless we restrict the expansion or compression. So it's very much related, but it's a little different in the sense that the sigma, or the stress, is actually formed if we restrict the expansion in any way. So if we put an expansion crack between the two paving stones, as long as we don't fill up that expansion crack with the expansion itself, we have a situation where the stones will not buckle up against each other and no stress will be created. So it turns out that every material, you probably knew this if you thought about it, expands differently, or different amounts, I should say, with positive delta T's. And it's also, you could think of it as every material contracts different amounts with negative delta T's. So for example, one material, we don't design with this, however, if you look at mercury in a thermometer, mercury has very defined properties of thermal expansion. And so what do we routinely use mercury to measure? You already know this. Say it. Yes. Yes, exactly. That's why we use it in thermometers. We also use it in temperature gauges of all sorts. And the reason for, there's a couple of reasons for that. I'm going to sing the praises of mercury for just a few minutes before we get back to the nuts and bolts. But if you take an evacuated tube and you put mercury in it and the temperature increases, you will get a change in length that's positive, and you'll get a change in length that's negative if you decrease the temperature. The other thing that's really interesting about mercury is it has a vapor pressure such that it doesn't form into a vapor, so that you don't get, like if you do this with water, you can do this with water, but what happens is you'll get little condensation bubbles in the tube, and if you use mercury, that doesn't happen unless you really draw a pretty intense vacuum on it. So if you, under normal conditions, mercury will stay together without having condensation. And the other reason is it remains more interested in integrity with the other mercury rather than rising up on the sides of the tube, which is called a wettability situation, or wetting. So it wets, it sounds kind of funny to say, but mercury is self-wetting rather than, it preferentially wets itself rather than the tube. Whereas if, once again, if you put water or some other substance, you'll sometimes see that the meniscus will look like this, which means that the substance is more, has more affinity for the tube it's in than it does for itself. So this positive or concave up meniscus indicates that mercury wants to stay integrated with itself. And that's also why if you put mercury, if you just like break open a thermometer, mercury will tend to form into little balls. It will, instead of being like a big puddle, if you give it a chance, it has so much desire to stay with itself and stay away from the substance that it's on, or the surface that it's on. It'll actually form into spheres. So there's some really good properties about mercury for measuring temperature changes. The biggest problem with mercury, of course, is that it's highly toxic. And so it makes you, it's a neurotoxin, so people are exposed to mercury for a long time sort of lose their mental functions. So it's not really a good substance to have floating around in the atmosphere. So, and also it's liquid at normal temperature, so building with it is kind of out of the question. But all substances, whether they're steel, wood, concrete, will expand some amount due to increases in temperature, and will contract some amount based on decreases in temperature. And the amount that they do this is designated by the Greek letter alpha, and it is called the coefficient, coefficient, of thermal expansion. And I recognize that sometimes it's a contraction, but we refer to it as the coefficient of thermal expansion because when we put it into an equation, we can say that the change in length due to temperature is equal to alpha delta T times L, which is the original length of the structural member. So you can see, because length is positive, it doesn't make sense to have a negative length, that if alpha is positive, that means that if delta T is negative, del T is also negative. So even though we call it the coefficient of thermal expansion, we think of it as being a negative expansion if we have a negative temperature change. So it is possible that some odd materials would be the opposite, or that this number would not always be the same, but we'll just talk about materials where alpha is always positive and remains the same over whatever range of temperatures we're using. So this equation, then, we can also recall that epsilon is equal to del over L. So you can say that epsilon t is equal to del t over L, or alpha delta t L over L, where the lengths cancel out. And so epsilon, due to temperature, is just alpha delta t. This kind of makes it easier to see the dimensions of alpha, in that epsilon we know is dimensionless. So if delta t has dimensions of degrees, either Fahrenheit or Celsius, this has to be per degree Fahrenheit or per degree Celsius. So it's degree Fahrenheit to the -1 or degree Celsius to the -1, depending on what set of units you're in. So then here, of course, if you have alpha as being per degree, this is in degrees, so these two cancel out. Length has dimensions of length, and del has dimensions of length. So everything works together. But what happens if we restrain the expansion? So we can see how much something's going to lengthen. And there's no sigma associated with an unrestrained thermal expansion. But what if we restrain the expansion? Well, then we have an induced sigma. If, on the other hand, we restrain, and when I'm using expansion, I'm talking about it could be a negative expansion, which would normally be thought of as being a contraction. I'm just trying to be consistent with the terminology. If we restrain the expansion, we will induce a sigma. Okay, so in that respect, it's similar, however, not exactly the same as it is for the relationship between P and sigma. Okay. All right, so let's take a look at a problem, if I can find a quick one. Is that my computer making that noise? Okay, sorry about that. Somebody got the sound turned on. There are some other, let's take a look at two. All right, let's take a look at problem 239 in your textbook. And then I'll probably have you guys do 241 for homework, but I'll do 239 in class. And I'll go ahead and redraw this, but basically we have a polystyrene rod consisting of two cylindrical portions, A and B, restrained at both ends, supported this way. I don't want that one. This is, hang on a second. Hang on. I may have to go for something. Okay, here we go. This is more to my liking. We have problem 251 and problem 252. All right, so let me read through 251, and then we'll talk about some correlations. I'll have you do 250 as well, but I'll talk about what's going on there. I'll give you a little bit more insight after I do 251. So 251, a rod, it consists of two cylindrical portions, AB and BC, and it's restrained at both ends. Portion AB is made of steel, which has these characteristics. We have a modulus of elasticity and a coefficient of thermal expansion. And portion BC is made of brass, so it has these. Knowing that the rod is initially unstressed, determine the compressive force induced in ABC when there is a temperature rise of 50 degrees. Okay, so let's go ahead and draw out this picture. So we have AB and we have BC. All right, so basically what happens here is we increase the temperature by 50 degrees centigrade. And when we do this, this wishes to expand, doesn't it? And it'll push against the ceiling and against the floor. And when that happens, we will have an induced pressure, or an induced, let's just say an induced load of P and P prime, because the rod wishes to expand and yet it can't. All right. So what really happens here, and there's a good example of this, I guess I would say, if you take a look on, if you look at page 84, conceptual application 2.6. All right, what happens here is, if you think about it, we do a method where we pretend for a moment that either the ceiling or floor does not exist. And we say, if this were unrestrained, del due to temperature would be some positive number. But del due to P essentially pushes back negatively, and del total will be equal to 0. See what I mean? So if you think about it, AB tries to expand due to temperature, BC tries to expand due to temperature, but the induced reaction in the floor and the ceiling because of that expansion pushes back, and the overall deflection is equal to 0 unless we break the floor or the ceiling, which is not our plan. If we do, we have a whole other set of problems, and we can't solve them in mechanics of materials. So here's what we can say then. If del total is equal to 0, we know that that's equal to del due to temperature minus, essentially, del due to pressure, or del due to P, right? And that those things together add up to be 0. Or another way you can think about it is to say that del due to temperature is equal in magnitude and opposite in sense to del due to the induced load P. All right, well, del due to temperature is equal to alpha delta TL, and we have two pieces of that, don't we? We have in AB, and we have in BC. And equals del due to a load, which is PL over AE. And PL over AE in BC. And if you look at this equation, we know what our alphas are because they're given in the problem. We're also given a delta T, and we're given the lengths. So we have all of the factors over here. Over here we have the lengths, we have the cross-sectional areas, and we have the moduli of elasticity. So the only thing that we're missing is P. So what we're really solving for is what is the magnitude of P that will be induced by this temperature expansion. This also makes sense, like if we had a higher temperature expansion, P would increase, wouldn't it? So in other words, if we had if we were increasing the temperature more than 50 degrees, that we would be pushing harder against the floor and ceiling, so that the force that they push back with would be more. I was looking at something. The reason I paused, sometimes I start thinking about the equation before I finish actually speaking, which is never a good idea. So, but what I was looking at is we have L's clear across, but they're not the same, are they? Because AB is not the same length as BC. If they were the same, we could cancel them out, just remove them from the equation entirely. But they are not the same length in this problem. All right, so let's go ahead and work this out. Let's put in some numbers, see what we come out with. Okay, for AB, which is the top length, we are told, I'm going to write these down here. AB is steel, and alpha in AB is equal to 11.7 times 10 to the negative 6 per degree centigrade. And alpha in the brass is 20.9 times 10 to the negative 6 per degree centigrade. Now the first thing I want to point out is the magnitude of these are always quite small, because you really don't have like something double in length due to temperature. It's always a very, very small expansion. So if you, or contraction, if we're going to talk about it in the negative sense. But so when you look at this equation, you need a big change in temperature to affect a little bit of change. All right. We're also given values of modulus of elasticity, which we will need for the right-hand side of the equation. So the modulus in steel is 200 gigapascals. And the modulus in brass is 105 GPa. All right. So let's go ahead and work this out. What we want to do is to solve for P. Okay, the first thing is, algebraically, this P and this P are going to be the same, aren't they? If you look at the rod, there's no applied force here. There's nothing that's going to change. I mean, P at the ceiling has to equal P prime at the floor. So if you do a cutaway here and you do a cutaway here, the P value is going to be the same. So that means that we can factor it out here. And we can write this as alpha delta T. Oh, and we can also factor out delta T, right, because it's the same. So we could say delta T times alpha L in AB plus alpha L in BC. Here's this side, equals P, same, and I can just divide it by L over AE in AB plus L over AE in BC. Okay. And now we can just solve for P. We've got to work out our units, which is one of the reasons I want to go through this problem step by step. So I am told that my temperature change is a rise of 50 degrees. So delta T is 50 degrees Celsius. I multiply that by the quantity. Wish I could, let me pull this down. Hang on. Nope, that's as wide as it goes. Okay. So for AB, this is 11.7 times 10 to the minus 6 per degree Celsius times L, which is 250 millimeters, which I'm going to write, because I want to keep everything in base units. So 250 times 10 to the minus third meters, okay? Plus alpha, which is 20.9 times 10 to the negative 6 per degree centigrade, times this length, which is given as 300 millimeters. So 300 times 10 to the minus third meters. Divided by the length of AB, which once again is 250 times 10 to the minus third meters over the cross-sectional area. I'm told that my diameter is 30 millimeters. So the cross-sectional area of AB is 30 times 10 to the minus third meters. That's my D squared times pi over 4. And my diameter here is 50 millimeters. So the area of BC is 50 times 10 to the minus third meters squared times pi over 4. Anyone have a good calculator? Tell me what those areas are in square meters right away. Is that what you got? Please check my work, because
You can't see it.
you can't see it? Oh, how's that? Is that better?
Perfect.
Thank you. It's one of those things that should be easy, but it's not. Do those look right, John? Okay. So for here, we put this here, we have 7.07 times 10 to the minus 4 meters squared times the modulus, which is 200 gigapascals, which is 10 to the ninth. That would be in newtons per meter squared. So there's the good news. My meters cancel out here. Plus 300 times 10 to the minus third meters here over my area, 1.96 times 10 to the minus third meters squared times the modulus 105 gigapascals, which is 10 to the ninth Newton per meter squared. Okay. And all of that mess equals P. And then we get to see if all of our signs and units and everything come out correctly. So let's go ahead and do the numerator first. And the units on, I'm going to leave the 50 out here. And so I'm going to take 11.7 times 10 to the 6, negative 6, pardon me, 11.7, and multiply it by 250, and that comes out to be 2925, and it would be times 10 to the minus 9th, 29. And if I make mistakes in my algebra, please let me know, because I'm not doing it to be cute. I'm doing it because I have an inadequate calculator here. Plus, I have 20.9, 300. This turns out to be 6270, also times 10 to the negative ninth. And my units are meters per degree Celsius or degree centigrade. So if I add those two together, 6270 plus 2925. So my entire numerator here is, I'm going to go ahead and rewrite this even though I didn't finish it off. 9195 times 10 to the minus ninth meter per degree centigrade. And I can actually just multiply this through the numerator, can't I, before I start messing with the denominator. So if I multiply that by 50, that gives me, hang on, this whole numerator becomes 459,750 times 10 to the negative ninth, and then I have degree centigrade in the numerator and in the denominator, so this just becomes meters. If I count back 1, 2, 3, 4, 5, I'm just going to leave it like that for now, but I could reduce that as well. All right, so let's go up here. I just want to mess with each one of these pieces. What I see is meter squared cancels meter squared. And what I'm left with is a meter per Newton in each of the terms of the denominator, which I can see is going to go very well for me when I get to the point where I'm actually doing some arithmetic. So if I have 250 times 10 to the negative third, and I divide that by 7.07 times 10 to the minus fourth, and again by 200, I get 0.1768, and that's 3, so that's 1. So is that minus 8 times 10 to the minus 8? So it's negative 3, and that becomes a positive in the denominator, or in the numerator, so that's a 1. So that's positive 1. Positive 1 divided by 10 to the ninth is negative 8, isn't it? Okay, if I've got my, oh wait, that was my 9, sorry. This is my negative 8 right there. Okay, so let's take the second term, see what we come up with. 300 divided by 1.96 and divided again by 105, sorry. And here I get 1.458. And I have 3. This is -3, so that becomes 0. So this is times 10 to the -9. Okay, so I have to add those two together. So let's just bring this decimal place over and make that -8 so I can add everything together properly. Divided by 10, and then add this plus 0.1768. So I get in my denominator, after I go through all of that, 0.32257 times 10 to the -8 meter per Newton equals P. And then to finish this off, when I take this number and divide it by this number, hang on, I think I actually have a reciprocal key on here, that's nice, times 45, 97, 50. So I get this great big number, and then I have, here I have times 10 to the -9th. When I bring this up, it's times 10 to the -1. So my number is 1425260.6 times 10 to the -1. No, excuse me. Yeah, that's right. And that would be newtons. Boy, that's it. Okay, I got it. Equals P. All right, so that means if I just bring that over to here, I get 1425226 newtons equals P, or I could call it 142.5 kilonewtons equal P. Okay. Now, I'm not sure if I've got all my arithmetic correct. I ran the units and I ran the numbers, and I think I did. But the calculator, I'm sure you've seen this on your, let's see. I'm going to come over here to the podium PC. This is the calculator that I'm using. So you can see I don't even really have exponents. So I was doing them manually, you know, just, so if I'm off by a factor of 10, you will find that. You have much better computing power than I do today. So but that is the process. The big thing I really wanted to work through with you, I mean, I did definitely want to work through the numbers, but I also wanted to work through the decimal points and the units, okay? Because everything has to come out, and as you see, P, which is a force, comes out in newtons and then kilonewtons, and that's a good unit, isn't it? Okay. All right, so for your homework tonight, this will be a good model. This will help you. But I would like you to do problems 250 and 252 for homework. Now, 252 is going to work pretty much the same way as we just did on 251. Okay? It's a restrained rod where you have this time it's just oriented toward the walls, but it's the same thing. When you have a thermal expansion, the two sides, the two walls are going to push against points A and point C, and you're going to have an induced P. Okay? Now, 250 is slightly different, and this is going to lead us into a conversation later on about reinforced concrete. What we have is concrete with rebar inside of it. Okay? Now here, when we increase the temperature, what's going to happen is the concrete and the rebar have to expand the same amount, don't they? So it's not zero anymore. The total expansion is not zero, but the expansion in the concrete is the same as the expansion in the rebar. And so the concrete has a desire, so to speak, to anthropomorphize the concrete, to expand due to temperature, and then there's an induced force pushing it back. And it'll be the same and the opposite in the rebar. But the force, but the total amount of expansion, rather, in the concrete is going to be the same as the total amount of expansion in the rebar. So you'll just set it up, instead of del total equals 0, you can say del in the rebar is equal to del in the concrete, and that each of these is a positive del T in the concrete minus a del due to P in the concrete, del temperature rebar, del P in the rebar. Okay? And so that will be the setup. The ideas are still the same, but the setup is slightly different. All right, do you guys have any questions for me? All right, so 2 homework problems, and on Wednesday we're going to talk a little bit more about Hooke's law, which is the that idea of, well, we'll just talk about it on Wednesday. No point in bringing it up right now. All right, so get your homework done, and we'll see you Wednesday.